Hello, my curious friend, and a very warm welcome to the Deep Field channel. Tonight we're going to explore something that is right in front of your eyes, literally beneath your fingertips at this very moment, hiding one of the most mind-bending secrets physics has ever uncovered about the nature of reality. We will talk about the void that exists within everything you consider solid, the immense silence that dwells inside every object, every surface, every inch of your own body. But I promise to try and keep the subject from being so disturbingly fascinating that it keeps you awake. But before we dive into this silent mystery, I would love to know in the comments which corner of the world you are listening to me from tonight. And if you are feeling too lazy, just leave a simple hello. It might seem like a small thing, but that little gesture shows YouTube that our space is welcoming and helps us bring more tired minds here to relax with us. If you enjoy our scientific journeys, please leave a like and subscribe. And to those of you who are already part of our community, thank you so much. If you want to get even closer, consider becoming a channel member. Members get early access to videos before anyone else. The link is in the description. Now, wherever you are, find a really comfortable position. Drop your shoulders, relax your jaw, and let the weight of your body be embraced by whatever is supporting it. If sleep comes, accept the invitation. Let us begin. There is a surface you know very well. You ran your hand across it today, perhaps several times. It might be the screen you're using to listen to this video, the sheet covering your body right now, the armchair, the mattress, or the cold wall you touched when you walked into your home. This surface seems absolutely real. It feels dense, compact, resistant. When you tap it lightly with your finger, it responds with firmness, and your mind registers this as irrefutable proof that it is solid, concrete, and full. But what if I told you that this entire sensation is a carefully constructed illusion orchestrated by physics? What if the solidity you feel is not a real property of matter, but rather the result of invisible forces acting within a space that is, for the most part, completely empty? Not empty in the sense that something is missing, empty in the most literal and unsettling sense of the word. Empty like the space between stars, empty like the silence before the thunder. When physics looks at matter up close, very close, it finds not a solid, continuous substance, but a dance of tiny particles separated by immense distances relative to their own size. Matter, as we have discovered over the last century of scientific research, is almost entirely empty space animated by energy. Think for a moment about the atom, the fundamental unit that makes up everything in the material universe. Each atom has a dense, compact nucleus at its center, where almost all of the structure's mass is concentrated. And around this nucleus, at proportionally enormous distances, are the electrons. Now comes the part most people never truly absorb. If the nucleus of an atom were the size of an orange and you placed it in the center of a football stadium, the electrons would be orbiting in the outermost bleachers of that same stadium. And between the orange and the bleachers, there would be absolutely nothing, just empty space. This is the true scale of the interior of matter. The nucleus occupies an infinitesimal fraction of the atom's total volume. Physicists calculate that the atomic nucleus is roughly 100,000 times smaller in diameter than the entire atom. If you could squeeze all the actual matter out of the human body, eliminating all the empty space between the nuclei and the electrons, what remained would fit inside a grain of sand. Not a small pebble, a grain of sand. All the mass of a human being compressed until the empty space was removed would result in something you could barely see with the naked eye. And yet, you feel the mattress. And yet, the table is solid. And yet, the floor does not give way beneath your feet. This is because the solidity we experience does not come from matter filling space. It comes from forces. When you touch something, The electrons on the surface of your hand and the electrons on the surface of the object repel each other with a powerful electromagnetic force. Electrons, because they carry the same negative electrical charge, simply cannot tolerate each other's presence in extreme proximity. This repulsion is what your brain interprets as resistance, as texture, as solidity. What you feel when you touch something is not matter touching matter. It is energy repelling energy across the void. There is a principle in quantum physics called the Pauli exclusion principle, formulated by the Austrian physicist Wolfgang Pauli in the first half of the 20th century. This principle dictates that two electrons cannot occupy the same quantum state simultaneously in the same location. It is a fundamental prohibition of nature. It is not that electrons do not want to overlap, it is that physics simply does not allow it. It is as if there were an invisible, unbreakable law preventing matter from collapsing in on itself. And it is exactly this law that ensures you do not sink through your chair while listening to these words. Think about how this completely reverses common intuition. We grow up believing that things are solid because they are made of substance, that the firmness of the world comes from something real and present. But physics tells us the opposite. The firmness of the world is a consequence of prohibitions and repulsions acting within the void. Solidity is an emergent effect of quantum rules applied to particles separated by proportional abysses of space. The most persistent myth about matter is exactly this, that it is solid in the popular sense of the word. The atoms are like tiny compact spheres that fit together to form objects. This image, while useful in certain educational contexts, is profoundly misleading when taken seriously. Atoms are not solid spheres. They are structures with more space than presence, with more absence than substance. Another common myth is that electrons orbit the nucleus like planets around the Sun, in well-defined, predictable circular orbits. This image, popularized in the early 20th century by Niels Bohr's model, was useful as a starting point. But quantum mechanics has replaced it with something much stranger and much more beautiful. Electrons are not in defined orbits. They exist in clouds of probability called orbitals, regions of space where they are more or less likely to be found if you make a measurement. An electron does not have a fixed position while it is unobserved. It exists in a sort of probabilistic fog simultaneously in multiple possible states until an interaction forces it to assume a specific position. This means that the electrons making up the atoms of your body at this very moment are not in defined places. They are probability distributions fluctuating around nuclei, forming patterns that physics describes with elegant equations, but that completely defy any intuitive visualization. Your arm, your hand, your fingers are composed of these overlapping, interacting probability clouds. You are, in a sense, made of possibilities rather than certainties. The number of atoms that make up an adult human being is of a magnitude that human language can barely accommodate. We are talking about something on the order of a 7 followed by 27 zeros, roughly 7 octillion atoms, and each of these atoms carries within it this absurd proportion of emptiness. The nucleus of each atom occupies a minuscule fraction of the total space. Everything else is absence. The atoms that make up your body are primarily hydrogen, oxygen, carbon, and nitrogen. Hydrogen, the simplest of all, has just one proton in its nucleus and one electron at a proportionally enormous distance. Oxygen has 8 protons and 8 neutrons in its nucleus, with 8 electrons distributed in shells around it. Carbon, the foundation of all the biochemistry of life, has 6 of each. They all follow the same architecture, a tiny nucleus surrounded by an immense void punctuated by electrons that are themselves essentially without detectable size. The protons and neutrons that form the nucleus are not, in turn, fundamental particles. They are composed of quarks, even smaller particles that interact via the strong nuclear force, the most powerful of nature's fundamental forces. And quarks, as far as current physics can determine, are truly sizeless, mathematical points without spatial dimension, fundamental particles with no interior. Matter, when you descend to its most basic known components, becomes less and less substance and more interaction, less and less a thing and more an event. There is something profoundly poetic and slightly disorienting about contemplating this reality while you're lying down or sitting, your body resting on a surface, gravity anchoring you to the ground, everything seeming so concrete, so immediate, so unquestionably real. And it is real. But what we call reality, physics suggests, is a structure built upon a substrate of animated vacuity. The appearance of fullness is woven over a tapestry of absence. When light crosses your room right now, it passes between the atoms of the air without difficulty, because the air, like all matter, is vastly more empty than it is filled. When the temperature drops and you feel the cold, what you are feeling is the transfer of kinetic energy between particles that never touch in the classical sense of the word. When you breathe and oxygen enters your lungs, molecules made of these almost entirely empty atoms combine with other molecules in your blood in reactions that sustain every beat of your heart. All of this happens on a substrate of empty space. The chemistry of life, the physics of the world, the texture of everyday reality emerge from interactions between entities that are, in their geometric essence, almost entirely nothing. And here we reach a frontier worth pausing to contemplate. If matter is almost entirely empty, and if what seems solid is actually a set of forces and probabilities dancing in space, then where does the energy come from that keeps all this in motion? Where does the animation come from that prevents the electrons from collapsing into the nuclei? What fuels this perpetual dance that happens inside every grain of sand, inside every cell of your body, inside every atom of the pillow, touching your face right now? The question of where this energy comes from is not new. It inhabited the minds of people who spent entire nights staring at candle flames, trying to understand why fire burns without anyone pushing it, why heat spreads without anyone conducting it, why planets orbit without any string holding them. For centuries the answer seemed hidden behind a veil that human language simply could not pierce. The Greeks imagined essences, alchemists imagined hidden substances, medieval philosophers imagined divine forces. All of them were, in their own way, trying to name something they felt existed but could not see directly. They were trying to touch the source. Imagine a compressed spring inside a closed box. You cannot see the spring, but you know something is stored there, something waiting, something with the potential to act. Now imagine that this spring never fully releases, that it lives in a state of perpetual tension, that the very structure of the box prevents it from expanding beyond certain limits. The energy is there, trapped, defined by the space that surrounds it, limited by the geometry of confinement. The electrons inside atoms live in something akin to this, although the analogy must soon be abandoned, because what truly happens is much stranger and much more beautiful than any spring in any box. The source of energy that keeps electrons in motion is not external. There is no hidden motor. There is no battery that will one day run out. The energy comes from the very quantum nature of reality, from a principle so fundamental that it seems impossible to accept the first time you encounter it. This principle states that position and velocity cannot be known simultaneously with arbitrary precision. If you know exactly where something is, you cannot know exactly how it is moving. If you know exactly how it is moving, you cannot know exactly where it is. This is not a limitation of our instruments. It is a feature of reality itself. Werner Heisenberg arrived at this conclusion on an island. Literally. He was suffering from severe hay fever in Göttingen and decided to travel to the island of Heligoland in the North Sea to breathe cleaner air. It was 1925 and Heisenberg was 23 years old. On that windswept island, without books, without colleagues, with only pads of paper and the mathematics he carried in his head, he began to develop the foundations of quantum mechanics. When he realized what he had found, he became so agitated he could not sleep. He went for a walk across the island in the middle of the night and sat on a cliff looking out at the dark sea until dawn. He had touched something true. The uncertainty principle, as it became known, has an immediate and powerful consequence for the interior of atoms. If an electron were completely still, we would know exactly where it is and exactly what its velocity is, which would be zero. This would violate the principle. Therefore, electrons cannot be completely still. They are compelled by the internal logic of reality to always have some movement, some uncertainty in position, some uncertainty in velocity. This mandatory minimum energy has a name: 0-point energy. It is the energy of the vacuum, the energy of the nothingness that is never completely nothing. This idea has implications that ripple through all of physics like waves on a lake. The vacuum, the seemingly empty space between particles, is not a sterile void. It is a place where particles pop in and out of existence on timescales so small that no instrument is capable of capturing them directly. They are particle-antiparticle pairs born from nothing, existing for a fraction of an instant measured in units so small they would need more than 12 zeros after the decimal point to be written with any meaning, and then mutually annihilating, returning to silence. This phenomenon has an equally poetic and technical name: quantum vacuum fluctuations. But these are not just mathematical concepts, they have been measured. In 1948, a Dutch physicist named Hendrik Casimir proposed an experiment that seemed absurd in theory and became extraordinary in practice. He suggested that if you place two metal plates very close together, in a near-perfect vacuum, with nothing between them, they would attract each other, not because of electrical charges, not because of magnetic fields, but because the quantum vacuum fluctuations between the plates would be suppressed, while the fluctuations outside the plates would remain free. The vacuum pressure from the outside would be greater than the vacuum pressure from the inside, and the plates would attract. Decades later, the experiment was performed and the effect was confirmed. The vacuum pushes. Nothingness has force. The law governing the behavior of electrons inside atoms goes beyond Heisenberg's uncertainty. There is a second law, equally fundamental, that determines how electrons organize themselves and why they do not all collapse into the lowest available energy level. Imagine an auditorium where every chair has a numbered tag, and there is a rule that two absolutely identical people cannot sit in the same chair at the same time. Each chair must have at most one person, and if two people look alike, one of them must be different from the other in some way so that both can exist in the same place. Electrons follow a rule analogous to this. Wolfgang Pauli, an Austrian physicist with a temperament as sharp as his intellect, formulated this principle in 1925. Almost at the same time Heisenberg was on his island, Pauli was famous among his colleagues for being brutally honest about others' work, to the point that physicists of the time had an expression that something Pauli called "not even wrong" was worse than being simply wrong, because it meant the work was so confused it did not even deserve the effort of being refuted. But when Pauli arrived at his own principle, he reached something that transformed the understanding of all chemistry. The Pauli exclusion principle states that two fermions, which is the category of particles to which electrons belong, cannot occupy the same quantum state simultaneously. A quantum state is a complete description of a particle, its energy, its probable position, its angular momentum, and a strange property with no classical analogue called spin, which can be roughly understood as an internal rotation that exists in only two possible values. Two electrons can be in the same energy level if they have opposite spins, but a third electron would have to move up to a higher energy level. And so, the electrons stack up in shells, each shell with its own characteristic energy, each electron occupying its unique place in this hierarchy. This hierarchy is the reason chemistry exists. Without the Pauli principle, all the electrons in all the atoms would collapse into the lowest energy state, and all atoms would be practically identical in their behavior. There would be no carbon different from oxygen, no sodium different from chlorine, no periodic table as we know it. The variety of elements, the possibility of combinations, the existence of molecules, proteins, DNA, thought, all of this depends on a law that says identical particles cannot be in the same place at the same time. There is a third law that completes this set, and it was discovered by a young Englishman who was only 23 at the time, and so shy that his colleagues sometimes joked he only spoke once a year. Paul Dirac, in 1926, developed a version of quantum mechanics that incorporated Einstein's special relativity. The result was an equation he himself described as beautiful, which among other things predicted the existence of antimatter before any experiment had ever detected a single antimatter particle. Dirac's equation showed that every particle must have a counterpart with an opposite charge, and this was experimentally confirmed a few years later when Carl Anderson detected the positron, the positively charged partner of the electron in cosmic rays. What unites these three discoveries, Heisenberg's uncertainty, Pauli's exclusion, and Dirac's relativistic completeness, is a worldview where matter is made of entities that follow rules radically different from the rules of the visible world. These rules are not approximations, they are not pedagogical simplifications. They are the exact laws that govern the behavior of everything, from the electrons in the iron of your radiator to the protons in the iron core of the Earth. The fundamental imbalance that makes the atom work is a tension between two opposing tendencies that never completely cancel each other out. On one side, the electromagnetic attraction between the negative electron and the positive nucleus pulls the electron inward, close, toward collapse. On the other side, the uncertainty principle demands that an electron confined to a very small space must have a very large kinetic energy, meaning it moves so fast and unpredictably that the electrical attraction cannot hold it in the center. This balance between attraction and uncertainty is what defines the size of atoms. It is what prevents everything from collapsing. The size of a hydrogen atom, for example, is not arbitrary. It is the exact size that results from the point where the tendency to collapse and the quantum resistance balance out. The number that describes this balance has a name, the Bohr radius, named after the Danish physicist Niels Bohr, who first calculated it in the early 20th century. Bohr imagined electrons in defined orbits, like planets around a tiny sun, and although this model was later refined and in some aspects abandoned in favor of a description in terms of probabilities and wave functions, it captured something essential, that electrons cannot be just anywhere, they can only be in certain energy configurations, and jumping between these configurations requires absorbing or emitting energy in exactly the right amount. When an electron absorbs energy and jumps to a higher level, it stays there for a very brief time before returning to the lower level, emitting the energy difference in the form of light. The color of this light depends exactly on the amount of energy released, which in turn depends on the specific energy levels of that particular atom. Each element has its unique energy levels, like a luminous fingerprint. That is why neon glows red, mercury blue-green, sodium yellow-orange. The light from street lamps, fluorescent tubes, and fireworks is the visible signature of the quantum states of electrons, the language atoms use to announce their inner nature. This mechanism of absorbing and emitting energy in discrete packets called photons is local and specific. It happens in a single atom, at a single moment, in a single location in space. The electron goes up, the electron goes down, the light is emitted. A tiny event, complete in itself, closed like a sigh. But this event does not happen alone. It happens in every atom that receives enough energy. And when this process repeats in a star, in billions of atoms per second, emitting photons in continuous cascades that travel through space for years, and reach the surface of a planet where other atoms absorb them and begin their own dance of levels, what happens when this repeats so many times that the scale of the phenomenon ceases to be atomic and begins to be cosmic? When a single electron emits a photon, that event knows nothing beyond itself. The atom has no awareness of the neighbouring atom. The photon carries no message about what is happening a centimetre away, or a kilometre, or a light year. And yet, when these events multiply on scales that the human imagination can barely contain, something extraordinary emerges from the statistical silence of so many repetitions. An order appears that none of the individual participants ever planned. This is what physicists call emergent behaviour, and it is one of the most unsettling and most beautiful phenomena that nature offers to scientific investigation. Emergence is not a property of any isolated part of the system. It is born from the interaction between the parts, from the repetition of simple rules in sufficiently large numbers, from the silent accumulation of individual events that, on their own, mean nothing beyond themselves, but together build an architecture that none of them could have sustained on their own. The void that fills every atom, this predominant space that exists between the nucleus and the electrons, and that we studied in the previous parts, does not disappear when atoms organize into larger structures. It propagates, it expands, and at the same time it becomes invisible to us, because what we see are not the atoms individually, but the collective geometry they form. Think about what happens when carbon atoms join together. Carbon has a remarkable property among the elements. It can form 4 simultaneous bonds with other atoms, and this ability to connect in 4 different directions of 3-dimensional space allows it to build structures of a complexity that no other element can match. When carbons bond to each other repeatedly in a specific geometry, with each atom occupying the center of an imaginary tetrahedron and its neighbors at the vertices, the result is diamond, a structure of extreme hardness, transparent to visible light, capable of dispersing that light into a spectrum of colors that for centuries fascinated kings and lapidaries. But what is diamond? Examined by quantum physics, it is emptiness. It is almost entirely emptiness. Every carbon atom that makes up the diamond is, like any atom, a region of space where the void represents more than 99% of the total volume. And the extraordinary hardness of diamond does not come from the solidity of the atoms that compose it, but from the geometry of the bonds between them, from the way the electron orbitals overlap and create regions of shared probability between neighbouring atoms. This is a point that deserves prolonged attention, because it profoundly contradicts what everyday intuition tells us about hardness and solidity. When a diamond resists being cut by other materials, this resistance is not the resistance of compact solid matter opposing other compact solid matter. It is the resistance of organized patterns of void opposing other organized patterns of void. Hardness is an emergent property of geometry, not of substance, and this applies to all the materials we know. The hardness of a bone, the flexibility of a cell membrane, the rigidity of a steel pillar, the malleability of gold, all these properties that seem to speak to us about the intimate nature of matter are in fact properties of the organization of the void in different geometric arrangements. Geometry in this context is not a mathematical abstraction imposed from the outside to describe reality. It is reality. When 20th century physicists began to understand the structure of crystalline solids, what they found was that the macroscopic properties of materials depended almost entirely on the symmetry of the atomic arrangement, not on the chemical identity of the atoms involved. 2 materials composed of different atoms could have similar mechanical properties if their crystalline arrangements were geometrically equivalent, and 2 materials composed of the same atoms could have radically different properties if those atoms were organized in distinct geometries. Graphite and diamond are both made exclusively of carbon atoms. One is one of the softest materials we know, so soft it leaves visible traces on paper. The other is the hardest natural material that exists on Earth. The difference between them is pure geometry, pure organization of the predominantly empty space that each atom contains. In graphite, the carbon atoms are organized in flat layers, each atom bonded to 3 neighbors in a 2-dimensional plane, forming a network of hexagons that extends laterally while the layers stack on top of each other, bonded only by weak forces. This architecture allows the layers to slide past each other easily, and it is this sliding that gives us the property we call softness. In diamond, the same carbon atom bonds to 4 neighbors in 3 dimensions, creating a rigid 3-dimensional network where there are no slip planes. The consequence is maximum hardness. No new substance was created between graphite and diamond. No different atom was introduced. Only the geometry of the void changed. William Lawrence Bragg was 22 when, in 1913, he developed with his father William Henry Bragg the technique that allowed for the first time the mapping of the arrangement of atoms inside crystals using X-rays. The idea was elegant. X-rays are electromagnetic waves with wavelengths comparable to the distances between atoms and crystals, and when these rays penetrate a crystal and reflect off the atomic planes, they interfere with each other in ways that depend precisely on the geometry of the atomic arrangement. By analysing the interference patterns, the Braggs were able to deduce where the atoms were. It was the first map of organised void, the first image of the invisible architecture that sustains the appearance of solidity in the world. What these maps revealed was surprising even for those who already suspected the atomic structure of matter. The regularity was absolute and universal. Every crystal of halite, regardless of where in the world it was collected, showed the same alternating arrangement of sodium and chlorine ions in a perfect cubic lattice. Every quartz crystal showed the same helix of silicon and oxygen atoms repeated in 3 dimensions. Nature did not invent different arrangements for each sample of the same mineral. It obeyed rigorous geometric rules, and the empty space that made up more than 99% of each atom organized itself into these networks with a precision that no human architect could replicate on a comparable scale. The discovery of X-ray diffraction opened a window that remained open throughout the 20th century and remains open today. Through it, scientists were able to see not just mineral crystals but proteins, viruses, DNA molecules, synthetic materials, superconductors, and medicines. In each case, what the technique revealed was the same fundamental phenomenon. Void organized into geometric patterns that completely determined the behavior of the substance on a visible scale. The 3-dimensional structure of a protein, obtained by X-ray diffraction, determines which molecule it fits with, which chemical reaction it catalyzes, whether it will transport oxygen in the blood or build part of a muscle or signal between neurons. And this structure is entirely a matter of how the void of its atoms arranges itself in space. But large-scale organization is not limited to the static geometry of crystals. There is another type of order that emerges from local quantum mechanisms, and this order is dynamic, rotational, dependent on movement. When we consider not just the position of the atoms but also the quantum state of their electrons, we find that in certain materials the magnetic moments of the electrons, a property we call spin, can spontaneously align in the same direction across domains of billions of atoms. This collective alignment is what produces magnetism in permanent magnets. Each electron has a magnetic moment that arises from a quantum property with no classical analogue, spin, which can assume only 2 possible states, up or down in whatever direction we choose to measure. In a magnetic material, the quantum interactions between neighboring electrons favor their spins aligning in the same direction, and this alignment propagates over long distances, creating magnetically ordered domains. The French physicist Pierre-Ernest Weiss proposed in 1908 the existence of these magnetic domains long before quantum mechanics existed to explain them. He noticed that magnets could be demagnetized by heat and remagnetized by external fields, and concluded that the internal structure of a ferromagnetic material must consist of smaller regions, each already magnetized to the maximum, but oriented in different directions so that the total field cancelled out. Experimental confirmation came decades later, when it became possible to directly observe the walls between magnetic domains. But the deep reason for the alignment within each domain, the explanation of why the spins of neighbouring electrons prefer to orient in the same direction, would only come with quantum mechanics. It lies in the Pauli exclusion principle and the exchange interactions between electrons, purely quantum phenomena with no equivalent in classical physics. This example of magnetism illustrates something that goes beyond curiosity about refrigerator magnets. It shows that the quantum states of individual electrons, the states we discussed when talking about electrons jumping between energy levels and emitting photons, do not exist in isolation. They influence each other through long-range quantum interactions. The quantum state of an electron in an iron atom may prefer to align with the state of an electron in a neighbouring atom, and this preference multiplies in a cascade through billions and billions of atoms until it creates something we can hold in our hand and see working from a distance. The local and the global are connected by a chain of quantum influences that spans all scales. Temperature is the great disruptor of these emergent orders. When heat is added to a system, it introduces random agitation into the movements of the atoms and the states of the electrons. This agitation competes with the ordering interactions. In the case of magnetism, there is a characteristic temperature, different for each material, above which thermal agitation destroys the alignment of the spins and the magnet loses its magnetization. This temperature is called the Curie temperature, named after Pierre Curie, who discovered it. Below it quantum order wins, above it thermal disorder wins. The boundary between the two regimes is a phase transition, similar in its logic to the transition between ice and water, but governed by quantum mechanisms instead of mechanical ones. Phase transitions are privileged windows for observing the competition between order and disorder on scales that span from the quantum to the macroscopic. Exactly at the transition point, the system exhibits patterns on all scales simultaneously, what physicists call critical behavior. Ordered domains of all sizes coexist, from groups of a few atoms to regions spanning macroscopic portions of the material. At this critical point, the distinction between local and global temporarily collapses. Everything is connected to everything else through correlations that extend over arbitrarily long distances. It is as if, for a moment, the entire material becomes a single quantum object. Kenneth Wilson received the Nobel Prize in Physics in 1982 for developing the mathematical theory that explains critical behavior, the so-called renormalization group. Wilson's central insight was that the properties of a system near a phase transition do not depend on the microscopic details of the individual atoms, but only on certain general characteristics such as the dimension of space and the type of symmetry involved. This means that completely different systems, made of completely different materials, exhibit mathematically identical behaviors near their phase transitions if they share these general characteristics. Universality, the fact that the same mathematics describes seemingly distinct phenomena, reveals that large-scale organization obeys laws that transcend the local quantum details from which it emerges. There is something profoundly unsettling about this. The quantum void of each atom, organized into patterns that are simultaneously local and global, produces properties that seem to transcend the components that generate them. The hardness of diamond is not in any individual carbon atom. The magnetization of a magnet is not in any individual electron. The order we see on a large scale is real, it is measurable, it has practical consequences, but it does not belong to any of the parts that compose it. It belongs to the relationship between those parts, to the pattern of organization of the void into geometries that space allows but does not demand. And these patterns, so elegant in their regularity, so robust in their persistence against perturbation, so universal in their mathematics, would be fundamentally simpler to describe, easier to understand, poorer in their variety, if it were not for the existence of an ingredient that the universe discovered late, but that transformed everything it touched, an ingredient capable of creating new layers of organization over the ones that already exist, of using quantum regularities as raw material to build something that physics alone could never have predicted. That ingredient is life, not in a poetic or metaphorical sense, but in the most technical and unsettling sense the word can carry. Life is the process by which the void learned to reorganize itself with intention, or at least with something that mimics intention with disturbing fidelity. It is the mechanism by which quantum regularities, those elegant geometries that space allows but does not demand, were captured, stabilized, reproduced, and progressively refined over a time that the human mind cannot truly visualize. 4 billion years, not as a number, but as a duration. 4 billion summers, 4 billion cycles of fusion and gravitational collapse in the heart of the sun, 4 billion complete rotations of this planet around a star that is itself made of the same organized void we are describing. Life seems simple when looked at from afar. A cell is small, a virus is even smaller, a molecule of adenosine triphosphate, the universal fuel for almost everything that moves in living beings, fits inside a space that the most powerful telescope of antiquity could never have resolved. But the apparent simplicity is an illusion created by scale. When you descend to the molecular level and begin to understand what is happening in there, the impression you are left with is not one of simplicity. It is of a complexity so profound, so stratified, so interdependent, that the very word complexity seems inadequate, like calling the ocean wet. What life did, and this is what makes it the most extraordinary amplifier the universe has produced, was to create structures capable of using the void in a directed way. Every physical system interacts with the quantum void, with the fields that permeate space, with the fluctuations that never cease even at absolute zero temperature. But these systems interact passively. A granite stone, with all its crystalline structure, with all the elegance of the bonds between silicon and oxygen, merely exists within the void. It does not use the void. It does not extract information from the void to modify its own future behavior. Life does exactly that. The membrane of a bacterial cell, that almost incomprehensibly thin boundary between the inside and outside of the simplest living being we know, is a structure of a double layer of molecules called phospholipids. Each phospholipid has a head that loves water and a tail that hates it. When placed in an aqueous environment, these molecules spontaneously self-organize into a double-layer membrane, because this minimizes the energy of the system. This is physics. This is thermodynamics. This would happen with or without life. But life took this physical phenomenon and transformed it into something radically different. A selective boundary, endowed with channel proteins that open and close in response to chemical signals, that pump ions against concentration gradients using metabolic energy, that create electrical potential differences used to move molecules and trigger signals. The cell membrane is not just a structure, it is an information processor built with the tools of organized void. And here is the amplification mechanism that makes life so powerful: information. Non-living physical systems accumulate order, but they do not accumulate information in a functional sense. A salt crystal has extraordinary order, but that order does not represent anything about the environment other than the presence of sodium, chlorine, and water. The order of the crystal does not change the future behavior of the crystal in ways that increase its chances of persisting. The crystal dissolves in the rain, and does nothing about it. A living being, no matter how small, carries functional information. Its genetic material is literally an accumulated memory of 4 billion years of interaction with environments that killed those who were not suited and allowed those who were to reproduce. Every sequence of nitrogenous bases in the deoxyribonucleic acid of a bacterium is a fossilized record of problems that the ancestors of that bacterium faced and solved. The information is inscribed in the organized void of the molecular structure, and this information directs the present behavior of the organism in ways that increase its probability of persisting and transmitting that same information to the next generation. This is amplification because information copies itself. A carbon atom does not create other carbon atoms with the same structure as itself. A crystal can grow, but only because molecules from the environment adhere to it following physical laws, not because the crystal carries instructions to build crystals. Life carries instructions to build life, and these instructions are copied with a fidelity that, while not perfect, is high enough to maintain essential information over billions of years and imperfect enough to allow the variation that natural selection uses as raw material. The result of this amplification process is what you see when you look out the window or at your own hands. The green color of a leaf is a visible manifestation of quantum physics amplified by life. Green exists because chlorophyll molecules, built with an atomic precision that took hundreds of millions of years of evolution to refine, absorb specific wavelengths of sunlight, those corresponding to the red and blue of the visible spectrum, and reflect precisely the green. But chlorophyll does not absorb this light by accident, it uses it. The absorbed photon ejects an electron to a higher energy state, and this electron travels through a chain of proteins in the membrane of the chloroplasts in a way that, according to research conducted in the early 21st century, involves a quantum phenomenon called quantum coherence. The electron explores multiple paths simultaneously, like a wave, before collapsing into the most efficient path. The efficiency of photosynthesis in converting light energy into chemical energy is almost 90% for the photons that chlorophyll effectively captures, an efficiency that no human solar technology has yet managed to match. The green you see is the quantum void being managed by life with a sophistication that took billions of years to build. A bird's song is another of these manifestations. The bird vocalizes because muscles controlled by nerves that fire electrical signals based on ionic potential differences across membranes, squeeze a structure called the syrinx, which is the vocal organ of birds. The frequencies produced, the patterns of silence and sound, the amplitude and frequency modulations that make each species recognizable, are encoded in the animal's nervous system from a combination of genetic instruction and learning. Birds that sing learn their songs by listening to others of the same species, and there is a critical window of development during which the young brain is especially receptive to these acoustic patterns. The song you hear in the morning is the sonic expression of a pattern of information that has been transmitted and refined over generations, inscribed in the organized void of synapses and neural connections, and expressed as vibrations in the air that reach your ear and vibrate the ossicles of your middle ear with such delicacy that you can hear it from afar. The very consciousness that perceives the song is a manifestation of the same amplification process. The classifications scientists have created to describe life forms reflect, each in its own way, the history of how the void learned to organize itself into increasing degrees of functional complexity. Prokaryotes, a word that comes from Greek and means before the nucleus, are the simplest living beings. Cells without a separate compartment for their genetic material, without internal organelles delimited by membranes, with an organization that, compared to what would come later, seems austere. Bacteria are prokaryotes. Archaea, that mysterious group of microorganisms found in extreme environments like hot springs and hypersaline lakes, are also prokaryotes. But do not let the relative simplicity deceive you. A common bacterium processes information, responds to chemical gradients, moves directionally toward nutrients and away from toxins, divides in two when conditions are favorable, and carries with it the functional equivalent of all the accumulated knowledge of its ancestors. Eukaryotes, with a true nucleus, emerged about 2 billion years ago in an event that is still debated. The most accepted theory is that an ancestral cell engulfed another, and the two, instead of one destroying the other, established a partnership that persists to this day. Mitochondria, the organelles that produce most of the energy in the cells of all animals, plants and fungi, were once independent bacteria. They still carry their own genetic material, circular like that of a bacterium, distinct from the genetic material of the nucleus of the cell that hosts them. You carry in every one of your cells the descendants of bacteria that existed before fish existed. This partnership between two domains of life was the leap that allowed the increasing complexity that would eventually lead to multicellular organisms, and then to nervous systems, and then to the ability to be lying somewhere right now, listening to words about the void. Multicellularity itself arose multiple times in the history of life, independently in different lineages. This suggests that, given the tools eukaryotes already had, the transition to organisms composed of many cells was something the space of biological possibilities almost demanded. When cells begin to live together and specialize, each expressing a different subset of its genetic instructions in response to signals from the local environment, the result is tissues. Tissues organize into organs, organs coordinate into systems, and systems integrate into an organism that breathes, thinks, feels, and perceives the very space in which it exists. Each level of this hierarchy is a new layer of emergent organization, properties that do not exist in the components, but arise from their relationships, exactly as the hardness of diamond does not exist in any carbon atom, and the magnetization of a magnet does not exist in any electron. You can perceive these layers in yourself right now, if you let your attention rest on direct experience. Feel the weight of your body against the surface that supports it. This weight is gravity, acting on a mass of almost entirely empty atoms, organized into molecules, molecules into cells, cells into tissues, tissues into organs that are at this exact moment executing processes you do not consciously control. Your diaphragm moves, your heart contracts, your kidneys filter, your liver processes. All this happens without you needing to think about it, because the information necessary to coordinate these processes is inscribed in levels of organization much older than language, much older than self-consciousness. The heat you feel on the surface of your skin is the thermal expression of the molecular agitation of the organized void that you are. The air molecules that enter your lungs with every breath, mainly nitrogen and oxygen, are themselves organized void. And when the oxygen reaches the mitochondria of your cells and participates in the reactions that release energy from sugar, what is happening is a quantum dance of electrons being transferred between protein molecules in a process that, according to recent research, may involve quantum tunneling, electrons crossing energy barriers that classical physics would say are impassable, simply because at the quantum level barriers are probabilities, not walls. You breathe thanks to quantum tunneling. The void is not just the space between things, it is the mechanism by which things work. And here, at this point of understanding, something arises that deserves attention. This entire system, with all this sophistication accumulated over billions of years, with all the elegance of its quantum mechanisms, with all the robustness of its emergent structures, seems stable. It seems in equilibrium. Your heart beats in a regular rhythm. Your neurons fire in coordinated patterns. Your cells divide at the right rate to replace those that die. The ecosystem of your gut, with its trillions of microorganisms that outnumber your own cells, functions in a harmony that only becomes perceptible when it is disturbed. But equilibrium, in thermodynamics, has a specific and, in a sense, ominous meaning. True equilibrium is the state of maximum disorder, the state where all usable energy has been dissipated, where there are no more gradients to exploit, where the dance has stopped. What living beings maintain is not equilibrium, it is the opposite. It is a highly organized state of disequilibrium, maintained at the expense of a constant flow of energy that comes from outside, that originally reaches us from the sun, and that when this flow ceases, when the organization loses its access to the energy that keeps it far from true equilibrium, the system does not simply stop where it is. It begins to dissolve back into simpler patterns, into physics without life, into the void that existed before any instruction was written on it. The apparent equilibrium of a living being is a dynamic equilibrium, maintained by a constant invisible effort against the natural tendency of the universe to move toward disorder. It is a permanent tension between the tendency of the void to organize when it finds the right conditions and the equally real tendency of the void to dissolve organizations when the energy supply that sustains them is interrupted. And this tension, this invisible thread between organization and dissolution, between the pattern and the chaos that surrounds it, is more fragile than it seems when you look at a breathing body, or a growing forest, or a chorus of crickets on a summer night. That fragility is not a flaw in the design. It is the very condition that makes the existence of anything worth calling alive possible. A system that could never be undone would also be a system that could never be built in a different way, that could never respond, never grow, never find a more refined organization than the one it was born into. The possibility of dissolution and the possibility of increasing complexity are the same possibility seen from opposite angles. The void that can organize into a chorus of crickets is the same void that can undo that chorus when conditions change, and it is exactly these changes in condition, these transitions between states, that reveal the less calm side of the void in action. There is a point in any complex system where the behavior ceases to be smooth and begins to be abrupt. Physicists and mathematicians who study these systems have a name for this moment: critical threshold. Below this threshold, the system absorbs perturbations elegantly, distributes the impact, dampens the shock, returns to its usual state like a pendulum that swings and then stops. But when conditions cross this threshold, when the energy input exceeds a certain proportion relative to the system's capacity to dissipate it with order, something changes in the nature of the response. The system no longer absorbs, it amplifies, it reorganizes. It makes a transition to a new regime of behavior that did not exist before and was not predictable simply by observing the calm behavior that came before. Think of the steam rising from a pot of gently heated water. The water heats relatively evenly, molecules moving faster and faster, heat distributing through available paths. But a moment arrives where this regime can no longer handle the energy flow coming from the fire. The system needs to invent a new structure to transport this excess, and it invents. Convection cells appear, circular patterns of water rising in the center and falling at the edges, structures visible to the naked eye that did not exist anywhere before, and that appear out of nowhere when the threshold is crossed. The physicist Henri Bénard observed these cells at the beginning of the 20th century, and their elegance deeply disturbed the physics of the time, because they were an irrefutable example of order emerging spontaneously from heat, from movement, from the agitated void. These Bénard cells are a gentle, almost didactic case, but the principle that governs them is the same principle that governs the most dramatic phenomena the void stars in when placed under enough pressure. A tropical storm begins as a temperature difference between the ocean and the atmosphere above it. This difference exists all the time at certain latitudes, but when the sea surface temperature exceeds a certain value, when the air is humid enough, when the wind at altitude is not shearing the rising column of air, the atmospheric system crosses a threshold. Evaporation feeds convection, Convection feeds rotation. Rotation organizes pressure. Pressure intensifies evaporation. Each component feeds the others in a self-strengthening cycle. And where before there was diffuse humidity and inconstant winds, a coherent structure hundreds of kilometers in diameter emerges, spinning with an internal organization that defies the intuition of anyone who has never studied fluid dynamics. The eye of a hurricane is one of the most unsettling phenomena the void produces in intense mode. At the center of a system that at its edges carries winds capable of toppling structures, there is a surprisingly calm column of air with open skies and extremely low pressure. This calm is not an absence of activity. It is the product of a dynamic equilibrium so intensely maintained that it seems like rest. The air rising on the walls of the eye creates a relative vacuum that pulls air from below upward with such violence that the very movement prevents the outside air from collapsing inward. It is the void within the void, organization within organization, a pattern sustaining another pattern, in layers of complexity that fit together like the rings of a tree that grew under pressure. Humanity learned to observe these phenomena first with fear and then with instruments. The first barometers, created in the 17th century, were attempts to measure air pressure, but they revealed that pressure was not constant, that it rose and fell in ways that seemed, to observers of the time, almost capricious. It took decades of systematic observation to realize that low pressure and bad weather went together, that there were patterns, that the agitated void of the atmosphere had a grammar that could be read if you knew where to look. The first weather maps were revolutionary not because they predicted the weather accurately, but because they revealed that the weather had structure, that it was not random chaos but organization on a continental scale. Today, satellites observe the Earth from above with eyes that see in frequencies invisible to the human eye. Sensors measure temperature, humidity, wind speed, pressure, chemical composition, in vertical and horizontal layers with increasing resolution. Supercomputers solve the equations describing the movement of the atmospheric fluid on grids of points, separated by increasingly smaller distances, advancing the state of the system in increasingly shorter time steps. And yet, weather forecasting loses accuracy beyond certain days because the atmospheric system is fundamentally chaotic in the precise mathematical sense of the term. Small differences in initial conditions grow exponentially over time, and there is no instrument capable of measuring initial conditions with enough precision to eliminate this uncertainty. Edward Lorenz discovered this problem in the early second half of the 20th century, while running climate simulations on a primitive computer. He restarted a simulation from the middle, entering the rounded values the computer had printed, and found that the simulation followed a completely different path from the original. The difference between the printed values and the values stored in memory was less than 1 in 10,000. This tiny difference, propagated by the nonlinear equations of the system, had grown to completely dominate future behavior. Lorenz called this sensitivity to initial conditions, and the world came to call it the butterfly effect. The poetic image that the flap of a butterfly's wings in Brazil could trigger a tornado in Texas, not because the butterfly causes the tornado, but because the system is so finely balanced in its instability that any perturbation can be the factor that pushes a critical threshold in one direction or another. But instability does not only produce storms, it also produces rivers. The water that runs off the surface of the earth begins as separate trickles, each following the path of least resistance in the topography of the soil. But when these trickles converge, when the volume of water exceeds the soil's capacity to absorb and spread, a channel emerges, and the channel, once established, begins to deepen, because the concentrated flow erodes more efficiently than the spread flow, and the greater erosion deepens the channel, and the deeper channel concentrates more flow. And the system converges to a stable configuration where the physical structure of the river and the flow pattern within it mutually define each other. The river is not a sculpture made by water in rock. It is a dissipative structure, an organization sustained by the flow, which would persist only as long as the flow persists. The shapes of rivers also obey thresholds. In a low-flow regime, a river meanders gently, smooth curves that develop slowly over centuries as the water erodes the outer banks of the curves and deposits sediment on the inner banks. But when intense rains raise the flow above a certain threshold, the regime changes. The river no longer meanders, it braids, dividing into multiple intertwining channels, carrying sediment that would normally stay on the bottom, rewriting its own geometry in days or weeks what took decades to build. Geologists who study ancient deposits can read in these sediment patterns the history of rains from past eras, because the transition between meandering and braided leaves an unmistakable signature in the rock. Avalanches follow a similar logic of threshold. The snow that falls on a slope accumulates in layers, each layer with its own texture and density depending on the conditions in which it fell and the transformations it underwent later. As long as the cohesion between the layers is sufficient to resist the gravitational force, the snow remains static. But snow is a material that flows slowly even below the melting point, that undergoes continuous recrystallization, that can develop weak layers of large fragile crystals called depth hoar. When one of these weak layers is buried under heavier layers, the system accumulates tension silently, and when the tension exceeds the resistance of the weak layer in an instant that can be triggered by a skier, by a sound, by a simple temperature variation, the system collapses in a way that propagates in waves across the entire slope. A slab avalanche can mobilize millions of kilograms of snow in seconds, reaching speeds that exceed many vehicles on the open road, and the energy released is the energy that had been patiently stored in the structure of the snowpack during weeks or months of calm accumulation. While you rest, somewhere a column of moist air is crossing at this exact moment, the threshold that will transform it in the coming hours into something that does not yet have a name because it does not yet exist. Somewhere, a layer of snow is developing within itself the crystals that no one sees, and that contain, in their growing fragility, the promise of a violent transformation that will change the shape of a mountain. Somewhere, a trickle of water is finding another trickle, and from this confluence the beginning of a channel is being born that perhaps 1,000 years from now will be a river with its own name on maps that have not yet been drawn. The void does not sleep. It is always at some point on its trajectory between organization and dissolution, and some of these points are transitions, thresholds where the nature of the behavior changes in quality, not quantity, where the system no longer does more of the same but does something completely new with the same components. And what makes this aspect of the void especially intriguing is that these dramatic phenomena do not arise in absolute isolation. A storm that forms over the Atlantic is not just a local atmospheric phenomenon, it affects the temperature of the ocean's surface below it, which affects marine currents, which affect the climate of entire continents, which affect where forests grow, which affect how much carbon dioxide is absorbed from the atmosphere, which affects global temperature, which affects where other storms form. The intense systems the void produces when it crosses its thresholds are themselves components of larger systems that also have their own thresholds, their own instabilities, their own modes of calm and agitated behavior. The atmosphere and the ocean are not two separate systems that occasionally touch. They are two aspects of a single conversation that never stops, a continuous exchange of heat, moisture, angular momentum, and dissolved gases that happens on every square centimetre of the planet's surface simultaneously. The storm that forms over the Atlantic and that we mentioned carries with it the thermal memory of weeks of solar irradiation absorbed by the ocean, and when it eventually dissipates, it returns to the sea and the upper atmosphere an amount of energy reorganized in ways completely different from those in which it was received. The ocean is the main partner of the atmosphere in this dance, and understanding how they exchange energy is understanding why the Earth's climate is not simply hot or cold, dry or humid, but rather a collection of patterns that persist for decades and sometimes for centuries before reorganizing into completely new configurations. The ocean surface absorbs most of the solar energy that reaches the planet. Not all of it, because clouds reflect a considerable fraction back into space before it even reaches the water. But the portion that passes through the atmosphere and hits the marine surface penetrates to depths of a few tens of meters and gradually heats a layer called the poetic zone, the region where light can still penetrate with enough intensity to sustain the photosynthesis of phytoplankton. This heated layer is less dense than the cold water below it, and this density difference creates an invisible barrier called the thermocline, a boundary where the temperature drops several degrees per meter of depth, and that separates the warm surface waters from the cold deep waters that occupy most of the ocean volume. The thermocline is not static. It rises and falls as the seasons change, as the winds press the surface, as systems like El Niño reorganize circulation patterns across entire ocean basins. El Niño is perhaps the best documented example of how ocean-atmosphere coupling creates feedback cycles with consequences that spread across the entire planet. Under normal conditions, the trade winds blow from east to west along the equatorial Pacific, piling up warm water on the western side of the basin and exposing cooler water off the coast of South America, a process called upwelling. This temperature difference between the warm western Pacific and the cold eastern Pacific feeds the trade winds themselves, creating a self-sustaining system. But when this equilibrium is disturbed, when the winds weaken for reasons we do not yet fully understand, the warm water begins to slip eastward. Warmer water means atmospheric convection reorganizes, rains move to the central Pacific, the winds weaken even more, and more warm water moves east. The feedback amplifies the initial disturbance until the entire equatorial Pacific changes configuration. The consequences of this reorganization reach all continents. Severe droughts devastate Australia and parts of Asia, while torrential rains flood regions of Peru and Ecuador. The Indian monsoon weakens. North America experiences milder winters in some regions and harsher ones in others. The jet streams in the upper atmosphere shift, redirecting storms and pressure systems that would normally follow completely different trajectories. An event that begins as a slight weakening of the winds over a region of the Pacific ends up reorganizing precipitation patterns across entire continents for periods of 12 to 18 months. And all this emerges from the same fundamental process we explored before, from the way coupled systems amplify small perturbations until qualitative reorganizations become inevitable. The El Niño and La Niña cycle, which is the opposite phenomenon where the waters of the eastern Pacific become unusually cold, occurs on scales of 2 to 7 years, but it exists coupled to larger scale variations that unfold over decades. The Pacific decadal oscillation is a temperature fluctuation in the surface waters of the North Pacific that alternates between warm and cool phases over periods of 20 to 30 years, and that modulates the intensity and frequency of El Niño events in ways we are still learning to quantify. When the Pacific decadal oscillation is in a warm phase, El Niño events tend to be more frequent and intense. When it is in a cool phase, La Niña events dominate. The interaction between these two cycles of completely different timescales creates regional climate patterns that persist for decades and that influence agriculture, river levels, drought frequency, and species distribution in regions as distant as southern South America and the northeast coast of Africa. And beneath these decadal oscillations exists the thermohaline circulation, the ocean conveyor belt that moves water slowly around the entire planet over time, scales that reach 1,000 years for a complete cycle. This circulation is driven by density differences created by differences in temperature and salinity, hence the name thermohaline, from Greek terms for heat and salt. In the North Atlantic, the Gulf Stream carries warm, tropical water toward Europe and Greenland. As this water moves north, it cools, becomes denser, and sinks to the depths of the ocean, where it slowly flows back south and eventually to other oceans. This sinking process in the North Atlantic is the engine that keeps the current moving, and it is extraordinarily sensitive to the amount of fresh water entering the ocean from the melting of the Greenland ice caps. Fresh water is less dense than salt water, and if enough fresh water enters the North Atlantic, it can weaken or interrupt the sinking that keeps the thermohaline circulation active. There are geological records suggesting that the thermohaline circulation reorganized drastically during the last glacial period, with catastrophic climate consequences for Europe and vast regions of the world. In a period called the Younger Dryas, approximately 12,900 years before present, the planet that was gradually warming as it exited a glaciation experienced a sudden cooling of 5 to 10 degrees Celsius in parts of the northern hemisphere, and this cooling happened in a matter of decades, not millennia. The evidence in the Greenland ice cores shows the transition extraordinarily abruptly, reminding us that systems that seem to evolve gradually can reach thresholds beyond which change becomes rapid and irreversible on a human timescale, even if reversible on geological scales. The geological timescale introduces a completely different dimension to understanding the behavior of these systems. Over tens of millions of years, the planet has experienced episodes of warming and cooling so intense that life had to completely reorganize. In the Paleocene-Eocene period, approximately 56 million years ago, a massive release of carbon into the atmosphere raised global temperatures by 5 to 8 degrees Celsius over a few thousand years, a geological blink of an eye. The depths of the ocean warmed enough to dissolve the calcareous shells of the organisms that inhabited them. Tropical forests extended to latitudes where deserts and temperate grasslands exist today. And after 200,000 years, the planet gradually returned to previous conditions. The carbon was reabsorbed, the forest retreated, the climate reorganized. The system is resilient on scales of hundreds of thousands of years in ways that are completely irrelevant to any human civilization. This contrast of timescales is one of the most profound sources of intellectual disorientation that the study of climate produces. What is stable on one timescale can be completely unstable on another. A mountain that seems permanent and immutable to a human being is being actively eroded, lifted, and reconfigured on scales of millions of years. An ocean that seems constant harbors variations that unfold over centuries and that will determine whether entire regions of the planet remain habitable or not. A climate cycle that seems chaotic and unpredictable on a scale of decades is, on a scale of geological eras, a regular oscillation of glaciations and interglacial periods driven by the Milankovitch cycles, the periodic variations in the eccentricity of the Earth's orbit, in the obliquity of the axis of rotation, and in the precession of the equinoxes that alter the seasonal and latitudinal distribution of solar radiation in ways predictable decades in advance. The sensitivity to initial conditions we discovered when looking at individual storms manifests in different ways on each timescale. On scales of days, it manifests as the fundamental limit of weather forecasting that Edward Lorenz identified in his computer simulations in the early 1960s. The famous discovery that tiny perturbations in the initial state of an atmospheric simulation grow exponentially until they completely dominate the forecast in a matter of weeks. On scales of decades, it manifests as uncertainty about when and with what intensity patterns like El Niño will occur, even if we understand the general mechanisms well. On scales of centuries, it manifests as the difficulty of predicting precisely where exactly the thresholds of the climate system are, the tipping points beyond which irreversible reorganizations become inevitable. We do not know precisely at what temperature the melting of Greenland becomes self-sustaining, We do not know exactly at what atmospheric carbon concentration the thermohaline in circulation begins to weaken in a self-feeding way. We know these thresholds exist. We know approximately where they are. But the precision we would need to predict exactly when and how they will be crossed is fundamentally beyond what any instrument, any model, any observational technique we can imagine could provide us. This fundamental limitation is not a weakness of science. It is a discovery of science, one of the most important of the last century, the revelation that nature imposes limits on knowledge that are not a product of our current ignorance, but are intrinsic to the mathematical structure of the systems we are trying to know. Sensitivity to initial conditions is not something that will disappear when computers get faster, or when satellites get more precise. It is a property of nonlinear systems just as gravity is a property of mass. And recognizing this is recognizing that prediction has frontiers that are themselves part of what nature is telling us about how it works. And there is an extraordinary beauty in this that takes some time to be felt in all its depth. We are faced with systems that are simultaneously completely understandable in their principles and fundamentally surprising in their detailed behavior. We know the equations that govern the atmospheric fluid. We know the processes of energy exchange between ocean and atmosphere. We know the feedback mechanisms that amplify perturbations and those that dampen them. And with all this knowledge, with all the extraordinary sophistication of our computational models and observational instruments, we are still regularly surprised. A cyclone that should weaken intensifies. A drought that seemed over-prolongs for another season. A summer that models predicted as normal becomes the hottest on record. Surprise does not diminish understanding. It coexists with it in a way that invites us to a form of intellectual humility that is completely different from ignorance. It is not that we know nothing. It is that what we know is enough to reveal with increasing precision the exact contour of what we cannot know, and this contour has a fascinating shape, a geometry that reflects the deep structure of the very systems we're studying. There is something contemplative in this position, sitting before a system so large and so old and so intricately connected that no mind could contain it completely, but with enough conceptual tools to perceive the patterns that organize it, to recognize the thresholds that define its behavior, to feel the way complexity emerges from principles that are in themselves elegantly simple. The equations that describe the movement of a fluid are not different in principle from the equations that describe the movement of a single water molecule. The difference is only that when we aggregate billions of molecules, the system begins to behave in ways that no individual molecule could anticipate. And something in this process of aggregation, something in this passage from the simple to the complex, holds a secret we have not yet completely formulated. An underlying unity that connects not only the different scales of the climate system to each other, but that connects these systems to something more fundamental about how nature organizes itself in all the domains we know. There is a secret hidden in the way systems fold back on themselves. It is not a secret that reveals itself all at once, like a door swinging abruptly open, but rather a secret that unfolds in layers, like overlapping fabrics that light passes through one by one, revealing behind each veil a veil even more delicate, even more luminous. The void that permeates everything we touch is not just a passive property of matter. It is a living system, in the broadest sense of that word, a system that feeds back on itself, that corrects itself, that emerges, that collapses and reorganizes in ways that continue to surprise the most experienced physicists even after decades of study. Feedback is perhaps the most silent and most powerful concept in all of physics. When we talk about the quantum void, we're talking about a field that is not neutral, that is not inert, that is not simply waiting to be perturbed. The quantum void is a field that responds to itself, that influences itself through circular mechanisms of cause and consequence where the distinction between what perturbs and what is perturbed begins to dissolve. Virtual fluctuations create small distortions in the electromagnetic field, and these distortions in turn influence the probability of new fluctuations in a loop that extends indefinitely, that never stops because stopping would violate the very structure of quantum mechanics. But there are two types of feedback in this system, and the distinction between them is what keeps reality coherent. There are amplifying feedbacks, those that take a small perturbation and expand it, that make a local event resonate beyond its immediate boundaries, that connect the microscopic to the macroscopic in ways that seem disproportionate until we understand the mechanisms involved. And there are stabilizing feedbacks, those that dampen, that correct, that bring back to equilibrium the system that momentarily moved away from it. The tension between these two forces is what gives matter its appearance of solidity, its resistance to touch, its apparent permanence in a world that at its deepest level never ceases to fluctuate. When an electron in its atom absorbs energy and jumps to a higher level, there is an amplifying feedback in that event, a perturbation that propagates through the electromagnetic field around it that slightly alters the probability distribution of all other electrons nearby. Matter, seen this way, is not a collection of isolated particles, each in its own private space. Matter is a network of mutual influences, a fabric of overlapping feedbacks where each element affects and is affected by all others within its range of interaction. The void between particles is not separation. It is the medium through which these influences travel, the invisible substrate that makes the coherence of the world possible. Stabilizing feedbacks appear in a particularly elegant way in the behavior of atoms and molecules. When two atoms approach to form a chemical bond, the system does not collide indefinitely, does not compress without limit until the particles fuse into a single point. There is an equilibrium that emerges naturally from the interaction between attractive and repulsive forces, an optimal point of distance where the total energy of the system is minimal, where any movement in any direction would increase the energy and therefore be resisted. This equilibrium distance is not imposed from the outside. It emerges from within the interaction itself, from the dance of the electron clouds overlapping, mixing, sharing their probabilistic presence in a region of space that before belonged to one and now belongs to two. And here we reach the molecular dimension, that level of organization that sits exactly on the threshold between the purely quantum and what begins to seem classical, between the behavior of individual particles and the behavior of objects with shape, with geometry, with properties we can touch and measure with macroscopic instruments. A molecule is something extraordinary precisely because it exists on this threshold. It is not large enough to behave like a classical object, but it is not small enough to be described by a single, simple wave function. It is a complex quantum system, a collection of nuclei and electrons all interacting with each other through that void that separates them, all contributing to a global wave function that determines the geometry of the molecule, its dipole moment, its reactivity, its color, its smell. The geometry of a molecule is perhaps the most palpable example of how deeply abstract rules produce concrete sensitive consequences. The exact angle formed by the two bonds in a water molecule, those 104.5 degrees that define its hook shape, was not chosen. It emerged. It is the inevitable result of energy minimization in a system where the non-bonding electrons of the oxygen exert repulsion on the bonding electrons, pushing the bonds closer to each other until an equilibrium is established. This angle, which seems so arbitrary, so specific, so unlikely to have been predicted a priori, is actually the direct expression of principles that apply universally to all quantum systems. And it is this angle, this emergent geometry, that makes the water molecule polar, that gives it the ability to form hydrogen bonds, that explains why aqueous life is possible, why the ocean exists as it does, why you, who are largely made of water, have the consistency you have, When we look at matter as an integrated system, as something where each scale connects organically to the others, where the behavior of individual electrons determines the properties of molecules that in turn determine the properties of materials that in turn determine the phenomena we perceive with our senses, something begins to change in the way we perceive the simple act of touching. Your hand resting now, perhaps on a soft sheet, perhaps on the surface of a table, perhaps on your own chest accompanying the slow rhythm of breathing. This hand is part of a system that extends uninterruptedly from the oscillations of the quantum void to the neurological processes that allow you to perceive the sensation of touch. There is no real separation between these levels. There is only the same void organized in progressively more complex ways. Emergence is the name we give to the process by which this complexity is built. And the most fascinating aspect of emergence is not that it produces complexity from simplicity, although that is indeed admirable. The most fascinating aspect is that the properties that emerge often cannot be predicted or deduced from an isolated examination of the parts. The fluidity of water is not contained in any individual water molecule. The rigidity of diamond is not contained in any individual carbon atom. Consciousness, if we want to go that far, apparently is not contained in any individual neuron. Something happens in the passage from the one to the many, something that physics has not yet completely captured in its equations, a principle of organization that seems to emerge from the very act of aggregating, of connecting, of creating networks of interaction where before there were only isolated elements. And the quantum void, that silent protagonist of this entire story, is present in each of these leaps of emergence. It is the space where interactions happen. It is the field that photons cross when they carry information from one atom to another. It is the region where wave functions overlap and intertwine. Without it, without this seemingly empty space that actually boils with virtual activity, the interactions that produce emergence would be impossible. The void is not just the setting where the play takes place. The void is one of the main actors, invisible, silent, but present in every scene, in every transition, in every moment where complexity takes a step beyond itself. Deep down, everything you touch is empty simply because emptiness is the fundamental condition of existence. Not nothingness, not the absence of something that should be present, but the active, dynamic, and creative substrate from which all matter, all energy, all form, and all experience are continuously woven. Every electron orbiting every nucleus of every atom in your body exists in a void that sustains it, that defines the limits of its presence, that provides the context without which its existence would be inconceivable. Every chemical bond that holds your molecules together happens through a void that does not separate but connects. Every sensation you experience, every texture your fingers perceive, every temperature your skin registers, is the result of fields propagating through this void, of forces crossing the seemingly vacuum space between particles and emerging on the other side as the irreducible richness of sensory experience. When we reconnect all the elements explored throughout this journey, that probability cloud that is the electron, the uncertainty principle that prohibits simultaneous positions and velocities, the exclusion principle that gives matter its impenetrability, the quantum vacuum fluctuations that make the void a place of permanent activity, the wave-particle duality that dissolves the boundary between the localized and the diffuse, the electrostatic force that makes two hands repel before they touch, the emergence of macroscopic properties from microscopic rules. When we reconnect all this, what appears is not a fragmented mosaic of disconnected phenomena. What appears is a single principle seen from many different angles. Reality is a field, and matter is that field in a state of temporary organization, taking forms that seem solid, that seem separate, that seem permanent, but that are, in their deepest essence, patterns of void, dancing with void. You are part of this. You always have been. Every atom in your body carries this constitutive void. Every molecule that composes you is a momentary configuration of fields that never stop oscillating. Every cell, every tissue, every organ, every thought that crosses your mind right now, at this moment when the words reach you in an increasingly distant, softer, more dissolved way on the edge of sleep, all this is made of the same substance that makes the stars, that makes the space between the stars, that makes the silence between sounds. You are safe. The universe takes care of you, not as a separate entity watching from the outside, but as the very structure within which you exist. The fabric that sustains you at every instant, the field from which you emerged and to which you return with every exhalation. While you rest, the electrons in your body continue their orbital dance. They continue tracing their paths of probability around the nuclei that anchor them. They continue participating in the chemical bonds that keep your molecules together. They continue being what they always were, presence and absence at the same time, localization and diffusion simultaneously, matter and wave in perpetual equilibrium. Everything is in order. The same forces that kept matter cohesive for billions of years continue their work now. The same fields that made the formation of the first atoms in the universe possible are the fields that cross your body while you breathe. You are not separate from this story. You are a chapter of it, a pattern that the cosmos generated within itself to be able, for a brief instant of cosmic scale, to contemplate its own depth. The void around you is not absence. It is presence of another order. Your eyelids weigh with the same softness with which probability clouds condense around nuclei. Your body relaxes on the surface that supports it, and this surface, which seems so solid, so reliable, so real, is also 99.9% space. Fields interacting with fields. Void recognizing void. You rest in the heart of matter. You rest in the heart of the void, which are the same thing. Let thoughts dissipate like virtual fluctuations that appear and disappear in the quantum field, each idea arising for an instant and then dissolving back into the silence from which it emerged. You do not need to hold on to anything now. You do not need to understand anything now. Understanding is also made of void, and the void does not need you awake to continue being what it is. You're safe. The universe takes care of you. Everything is in order. As you slip into sleep, the fields continue, the electrons continue. The quantum void continues its silent and eternal activity, indifferent to sleep and wakefulness, present before you and present after, the imperturbable foundation upon which all experience rises and to which all experience returns. You are part of this. You always have been. Good night. The universe continues its silent dance and we rest in its embrace. Thank you for walking with me tonight. Sleep well.